Hi. Good morning. Well, welcome back. I'm probably the third Chris on the stage, basically, in a row. Nice to be here for the first time in the US with hardwear.io. I've been presenting on previously in the Netherlands hardwear.io on fault injection attacks at Black Hat on white box cryptography. I've been exploring a number of ARM and MIPS based devices, and recently also Blue Hat with bypassed secure boot, an encrypted one without having a key. So more or less this describes in brief what I've been doing the last few years. A bit of TEs, which I've been giving to training recently. But one of my interests is also having applying odd attacks or something which might be in corners of what seems to be, let's say, practical or applicable in general to new context. So for example, I found extremely interesting the fact that we do have a trend of new devices, of course, in the last few years that are heavily connected, which aim to be low power, which aim to be portable, and so they don't have so much, say, requirements in terms of performance, in terms of CPU requirements. So basically, there may be a new kind of scenarios where all the attacks may apply to new context, and I wanted to explore the timing attack here. So I assume that everybody's familiar a bit with the timing attacks. Who is not? Wow, impressive, good, that's great. So that's a string compare plugin implementation. It's arriving. It's taken from an open source project uclipc. So basically, it's the latest version that is available on million devices at the moment. Okay, so nothing really strange here or fancy. The full source code available, so you can actually check what I'm saying here. Well, first let's check. Do you see any vulnerability over here? Is it vulnerable?
To timing?
Not to timing, at the moment. To something else. If you find something, please file a CV. I have not been able to find anything software-wise or logical-wise, okay? But as soon as we put in scope the number of situations where, well, I think that everybody is familiar with here, we have a problem here with early termination, of course, and then you have a timing attack. I'm going to explain that a bit earlier. So this means basically that this string compare function, by the way, the memcmp function is the same. The strings do not have anything special over here. So basically, the comparison is done characters by character. You see this here, basically, one by one, and it actually stops as soon there is a wrong one. Okay, this is a typical normal implementation for performance, and you don't need to compare the full strings. So what is the problem over here? Of course, that if I send a wrong character, which I don't know what it is, basically what happens is that the loop is done in this way. I just go through and through the while just exit directly, okay? So I don't know if this is a wrong character, I just send one, okay? Then I send by chance a good one. And then if I send by chance a good one, the loop that you actually see there is that you check the first one, the while actually says it's a good one, so basically you actually do the loop again. And then, because the second one that I sent is likely incorrect, it's just exit. So basically, I have a distinguisher in behavior. So the device or the target behaves differently if I send a good character or a wrong one, basically. Even if I don't know if it's good or one. So in principle, I am facing what is called the non-time constant software. It's a general problem. It's not only for this string compare. It's available in many other parts of software. And usually this is taken care of only in a situation where the side channel attacks or the kind of attacks, the threat model you are facing is actually included. Okay? So this code is presented now on millions of devices and no one is complaining about anything about it. So let's just make this clear. And I don't think generally it should be a concern in any cases, but let's see when this can be a concern. The point is that the timing differences that happen when I give a stimulus to a device actually can tell me something. in general. Basically, I give an input to the device and I just see the behavior, even if I don't know anything, basically. In this case, I can actually measure the time, the response time, because I can send a character and it takes 1 second, it's a wrong one. If I get a response of after 2 seconds, which actually is much less, of course, but the idea is that I sent the right character. Okay, I found the right one, so basically I can go to the next one. But in general, the timing difference may leak information on what is not directly observable, basically on what is available happening in a device or even in HSM, even in a smart card. So I'm talking about a general problem here. It can be used also as an oracle for testing assumptions model. Like, for example, I think that the software may behave in this way. Maybe if it behaves in this way, it has this timing characteristics. Instead, if it has another way, I can actually use that as an information for reversing what I don't know, or for adding information of what I don't know. So the requirement is that the time leak needs to be present on an observable channel. Of course, if you cannot observe the channel, you cannot make the measurement. So if you cannot make the measurement, you cannot take that information out. And of course, the measurement needs to happen with sufficient precision and accuracy. Everybody's familiar with the difference between precision and accuracy, right? Just to make make clear, you have precision when basically you have a very scale which is very precise and defined. For example, you have a nanosecond precision when I can tell something, distinguish one process from another with a 1 nanosecond precision. It doesn't mean that the measurement that I'm taking is accurate. So it doesn't mean that the value that I am measuring at the moment is actually the real value of that measurement. So depending where you take the measurement, you might have different degrees of precision, so because you have better counters, or a different degree of accuracy, depending on where you take. To give a small example, if I take the measurement with an FPGA on the network, basically, I have quite a high degree of precision, of accuracy, because I don't have the noise on the host, because it's directly on the network. I don't have scheduling of the kernel, I don't have any other things. But the precision depends basically on the speed of the FPGA. Vice versa, if I take a user space measurement, I have the real-time performance counters of the CPU. With that 4 gigahertz, they give me 250 picoseconds precision. But I have so much noise from the kernel scheduling, from the interrupt and so on, that my measurement is inaccurate. Okay? This is just to make things clear what I mean by precision and accuracy. So the basic idea in general is that you send a request. It might be any kind of probe. Try to think this in a general way. It might be an SPI request on an SPI channel. Okay? It might be anything on any channel where you can actually exert and send a request. And you measure the time from the response towards the victim. This is always a very good exercise regardless of what you're doing. For example, people are using timing correlation between SPI accesses and secure boot in order to have a good insight of what's happening during the secure boot by measuring the timing for accessing the SPI. So time gives you much more than just what time is it now. So basically you need to collect time measurement for the first character. You need to collect multiple requests for each candidate. That's obvious. Basically you need to group the requests. You need to choose an estimator and set the threshold. Like, for example, I'm counting, let's say, the average of this population, okay? And I say that these 2 characters are distinguished when they differ by, 10 microseconds. I've set an estimator, the average, and I've set a difference for the threshold. This is a general process. It doesn't change if you're doing that on network, remotely, locally. It will happen regardless. Unless you are in a very lucky situation where one measurement is already sufficient for telling the good from the bad, basically. The point is that telling the good from the bad, unfortunately, is something which is a bit underestimated. When you actually look at blog posts and all these things, people say, yeah, I can distinguish 1 character good from 1 character bad. Well, that's a very good start. Now start distinguishing 1 character good from 254 character bad. With all the noise, with all the measure, and then, if you are able to do that, then we are onto something. So the ability to distinguish then only the good and bad does not help you. You need to distinguish the good among the entire population or the other bad. So this means that your statistics needs to be quite relevant and strong. And this is a bit that is often, let's say, underestimated, I think, in 70-80% of timing attack articles that you see outside. But then you go to the next one, basically. What has been done until now? Well, relevant application have been the extraction of cryptographic keys, SQL injection, basically, remote password guessing, although not so much for a reason which we are going to discuss in a moment, and even NetSpectre with cache timing attacks. Some are quite exotic, some are quite practical. The SQL injection is actually used in the case of blind SQL injection, when you need to extract, let's say, table names and other field names and so on. I'm not an expert on this part, I leave this to other people. But what I'm an expert about is that for sure the time differences that you need to measure go between 1 millisecond and 1 second. So these are things which are 10 to the power of 6 slower than one CPU going at 1 gigahertz. So this is what we are discussing about. And these things are measurable over the network. What can we do now on the network nowadays? We can perform measurement, we can distinguish differences of 100 nanoseconds over the LAN locally. So if you are on the same LAN, we can take enough measurement for distinguishing processes of 100 nanosecond difference. While remotely, we can actually do at the most 1 microsecond. Do you have an idea why 100 nanosecond is the limit at the moment? I have some guess, but I would like to also hear your opinion, please.
It's about 100 megahertz.
In this case, it would be the 1 gigahertz probably, but I think you are onto something. Yeah. So the unfortunate part that this paper, this didn't specify the setup, so we don't know how they detect the measurement. But there is one thing: if you work on with a gigabit network, basically, there is something which is called with an Ethernet, something which goes the interframe gap. This means that you cannot put something on the network faster than the interframe gap. So this means that, if I remember correctly, it should be something like 960 nanoseconds, 140, bear with me, we're on there. So almost 1 microsecond for 100 megabit, and goes down to 96 or 94 nanosecond for 1 gigabit. So my impression, my expectation is that we reach those levels here, just because we are working a maximum with 1 gigabit. Because your sampling precision is not high enough, is at the limit of what you can actually measure, and then you can go up, basically. And this actually also explains a few things which I'm going to say after. So I'm glad that I'm not the only one thinking this. And if you have other ideas of why this is the limit at the moment, I would be glad to hear. So the point is the following, that you're working with a fast PC, which is over the network, which is a 4 gigahertz clock, for example. Now, it's not that rare. I mean, nowadays, you would expect something like that from an internet server. So this means that one clock tick is 250 picoseconds. To give you an idea, we are already almost 7 magnitude orders slower, so faster than that SQL injection. So this means that even if you are measuring something of the network on a browser, basically, you have a millisecond precision, and if on the other side they answer within half a second, you have enough precision for getting data. So that's why SQL injection, blind and timing, it is possible at the moment. But we have better stuff at the moment. So this means that if you take one single string compare loop, the one we actually looked at, and you compile that on x86, I know because I did it, you get 13 instructions, more or less. That at that speed, it takes more or less 3 nanoseconds. Assuming that you can do one instruction per clock cycle, which is a very weird assumption nowadays. So it's probably even faster than that. So basically we are in this situation that the state-of-the-art remote can measure 1000 nanoseconds or 1 micro. locally you can actually do that. And the PC is more or less like this. So no, I don't think we have enough precision. I would say that in environment where we might have 10 gigabit to 100 gigabit in the environment, you might have the right precision or even for do attacking that string compare locally between server. Keep in mind that I've done this attack instead between on the same host, two processes, and UDP socket basically, and it does not go through the Ethernet. So this means that I don't have the interframe gap at the moment. I was able to break this with the timing attack a password on a 4 GHz CPU between two processes. And this gives me confidence that it is actually the Ethernet channel that is possible. Maybe we can actually discuss that a bit later. It's not in this presentation, but it might be interesting if you have cross VMs processes that talks over socket and where you have just anything which is compared by a string compare or a mem compare, which is also, by the way, let me add here, is not a good design practice, of course. If you are actually doing an authentication, you should never use your password directly in your comparison. You should use much better than that. So if I would be attacking probably, I don't know, clouds and VMs over clouds, probably this would not be so much applicable, because I hope that people actually do design these things nicely, although you never know, of course. So basically I would say that I agree that with people with Morgan and Morgan, there are two different Morgans, the black hats, that says that it's impractical in vast majority of cases in 2015. But the case that they were considering and that the literature until now was considered are remote servers with fast CPUs or network connection. And on that part, I fully agree that I would not even spend 5 seconds on thinking of that. But we have another thing nowadays, which was not even there like 4 or 5 years ago. And still people in 2014 already, they said, yes, this indicates that timing attacks on regular string comparison have to be assumed feasible for any embedded system already in 2014. And that's where the search stopped. Nobody even looked at that even anymore on this stuff, basically. Keep in mind that being able to attack the string compare means to be able to attack any other situation where you are leaking times. Any. Because that's the fastest situation that you can have. Unless you do basically a comparison on an FPGA with an XOR in parallel and all these things, and then it's another point. But software-wise, if you're able to attack that, then all the other situations which are time-dependent becomes immediately feasible. Okay? So that's why for me it's a distinguisher. So if I can do that on an embedded device, on an IoT device, then all the other things become immediately available. Okay. So that was my interest basically. What you see here instead are a number of measurements that instead I've done the same string compare on a different systems. Okay. So this is the status of the state of the art for local. This is the line. If you are above this line, I can actually likely attack you with a 1 gigabit connection in the local LAN. Okay, so basically what you see here is that Netgear R7800 is 1.7 gigahertz, is like this. Keep in mind though that this guy has frequency scaling. So this can go down to 800 megahertz, so it goes up, of course, it goes lower. The Raspberry Pi here is 1.2. We are I think it's about 50 nanoseconds, one single loop. I still cannot do that. Although I would be curious to do that if Raspberry Pi had 1 gigabit interface. They don't have it. Unfortunately, that they have only 100 megabit, and that's the limiting factor, basically. But there is another one here. Let me check. This one is the SP32 at 240 megahertz, which is one of the widest microcontroller widely available nowadays in the world. It is nice because it has Wi-Fi which can go up to 160 megahertz, megabit per second, mistake. And this one can go from 240 megahertz to 160 to 80. So the value that you actually see here becomes twice and 3 times the value if you actually go down. And most people actually want to clock it down just because in order to save battery. So what happens for this device is that normally they are not available just because they are in low power mode. But as soon as they are up, basically, they become this low at 80 megahertz with an interface that can go up to 160 megabit per second. So that becomes interesting. The Arduino maker already is around the 600 nanosecond, 48 megahertz. And the Arduino Uno, which is the widest available platform on microcontroller in the world for doing projects, makers, fairs, and all small things, it runs at 16 megahertz. So this means that it's even above the remote thresholds, so I should be able to attack it. There is one caveat here. It's actually, this is a bit less than 1200. It's the resolution of the graph that was not that high. It is slightly above 1000, basically. And it has a 100 megabit shield. So I'm really at the boundary of what I can do. Let's see what can be done. So the point is that there are devices which are much slower than this. Much slower. The point is that you have a combination of a slower clock and fast network interfaces. The reason is that if you want to connect an older device to the network nowadays, so you have an old design, you cannot buy anything cheaper than 100 megabit. So if you want to connect an ICS controller, that project, that design, want to reuse that connected to the network, you are going to use minimum of 100 megabit. So this means you are connecting a 4 megahertz CPU with a 100 megabit Ethernet. And we are back to square zero because those devices have authentication for the coils, for the sensors, for accessing a number of interfaces, which are not probably that solid in terms of design. Okay, so this is basically the reason of my research. Because first, on this device, the single string compare loop, and even more, of course, is within the range of remote measurability. For sure, given. That's something that can be done. The point is that there is so much around in other contexts, like this, where there are older infrastructure that get connected to the network. Only in some cases you have the password protection, the authentication. But when you have it, it's usually not that solid. Okay? We are coming now to attacking this device probably in the next few slides. There are a few challenges though. The problem is that the target connectivity may not be sufficiently fast for reasonable attacks, where sufficiently fast means in ratio to your clock, of course, because that's exactly what we are talking about. There is acquisition noise, network, you change routes, there is buffering, buffer bloating, QoS, other delays. The target has problem with scheduling, bandwidth saturation, frequency scaling, clock drifts, and the same on the host side. And also, once you collect the data, you start to process the data, do statistical analysis. You might be introducing some biases in your machine learning models. You might have wrong estimators. You might have pre-processing using artifacts just because you eliminate some data. So there's also noise over there. The research has not focused so much on eliminating this part of the noise. Research has focused a bit on reducing the noise on the network, mostly. If you look at this picture, basically you see that even if you only send the command for measuring, you have some measurement that goes from user space. Already on the host, you have some noise, even when the packets actually exit. And this is what you actually see here. It's noise host forward, going out. It's on the network, we just discussed it, but even the victim, might have concurrent execution of processes and all these things. So there might be even there the challenge of doing that, okay? Same on the response. What you want to measure is only this part, while on this side is there is even much noise. The point that if you take only small time frames, very short, you may assume that the noise, so the delay under the short time frames are constant. You can actually make that assumption, and it's going to be very useful in a moment. So basically, in my test setup, I used an Arduino Uno with 16 megahertz, 100 megabit Ethernet shield, and the direct connection to host, because I didn't want to focus on network for a moment. People already worked on that. There are already a bit of solution we are already going to discuss. I took that implementation, put that in a UDP server, and that does the password authentication, nothing more. And the measurement that I take are taken at multiple path points within the host. We are going to discuss in a moment, initially from user space, like I send the packet. Before it exits the user space, I just start my timer. As soon as I receive it back, I stop my timer. As simply as that. Nothing more. And this is what you see in terms of timing distribution. What do you see? Which character? So basically what I did, I sent 10,000 probes for each character, number 3, 4, and 5, and so on. And I just plotted down the time that it took to come back, nothing more. So 500 packets took this much, other 500 packets took this much, only a few took this much. So there's already a point over there. Which one do you think it is the right character over there? It should be easy. The right character is the one that takes more, basically. So this means that the distribution is a bit skewed on this side, basically. So you see that the yellow here is a bit on this side. So if I had to choose one character, it should be probably the orange one, which is indeed number 3. This is the right one. This is basically how it works in situation where your delay is more or less 10 microsecond difference, so that every loop take 10 microseconds. And this is the situation, for example, of a 2 megahertz device, which may be a SCADA controller somewhere or a sensor somewhere. Okay? So if I'm able to measure that difference, well, then we come to the remotely in a moment, but we arrive at the remote part in our presentation. We're talking about remote at the moment. So here this is actually visible, and it's visible statistically, and it's visible because one character can be distinguished from all the other ones. So it's not 1 to 1, it's 1 to all the others. If we go to the 1 microsecond difference, I would challenge everybody to recognize which is the good one. Honestly, it's not visible, basically. You need to perform some analysis, basically. So 1 microsecond difference is in one single loop. It's not, or any other process is not really distinguishable at this level. You will probably need a different analysis or many more measurements in order to see a clear cut. But the more the measurement you take, the more time it takes, the more are the chances that your network is not stable and you get noise. So you want to be quick, sharp, and fast as much as possible. So basically, there is also another problem. The whole distribution are non-Gaussian. They are known. Actually, they are usually multimodal. They are quite skewed and so basically, they are generic distribution that have this kind of long slopes, which we don't know. We are not able to model at this moment. And there are very few estimators that we can apply to such distribution. So how do you compare these two strange things? The concept of average does not really help, because for some reason, they would not have even the same shape. The variance doesn't even make sense. There are many other estimators that are bound to the fact that you know your distribution, or that you can assume that. In this case, it's not. There are very few statistical estimators that can be applied. So this is not such an easy problem to deal with. One interesting one is the box test in 2009. crossed with others. So basically, this is a very generic estimator, maybe useful also for other projects, so that's why I'm explicitly mentioning this. So let's assume that you have two populations of the same distribution that you don't know, okay? For any given population, you can always calculate what is called the percentile. So where stands the 5%, this is the line, you see this line? Is the 5% of your population stands on this side, for the blue one. Let me stay here, maybe it's better. So on this side, this means this is the line where the 5% of your population stays here. And this is a concept that can be applied to anything, even if you don't know the distribution as well, okay? This is the line where the 7% of your population is on this side. So basically, for any given population, if you get to these numbers, you get a box, okay? So this means that you can create for every population these two boxes. And this is your estimator. Then you need to set your threshold. The threshold is that, given those numbers that I fix, which are arbitrary by experience and all these things, which may work or may not, but let's assume that I have chosen them, the distinguisher is, if the boxes do not overlap, then I say that they are different. If the boxes do overlap, I'm not able to distinguish them. Interestingly, this has been the estimator that worked best in the research of these guys. And they are the one that were able to measure the 100 nanoseconds, the limit. So they established the limit and they use this. So do not dismiss this just because it doesn't really work. Of course, we have progressed quite a bit. Well, basically, it would be nice if we can go back to a Gaussian distribution. It would be really nice because we can actually apply even machine learning. We can apply a lot of things and improve the quality of what we can do. So this means that we are in a situation where technology, you may need, 1 million measurements, for example, but because of the behavior of your distribution, you can go down to 10,000, maybe, by processing. So you can actually use differential pairs. Instead of doing one measurement, you send a reference, which can be anything. It can be wrong or bad, you just send a reference, and you take that measurement, okay? This is called ref. Then you actually do the measurement that you really want to take. If they are close enough, you know that they are under the same condition. This means that if you subtract them, the delta will be the difference. And the delta will be all the noise that we will not cancel out. So if you actually do this kind of differential approach, which is now quite clear, and if you don't see that in any timing article that is not mentioned, probably there is some work that needs to be done. The constant noise is cancelled out, and we are going to do that in a moment. And under some assumption, it can be Gaussian, basically. Let me show that first, how it looks like. You see that now it's centered at 0. So basically, it is symmetric. It is not really a Gaussian because there might be some additional user space, so it's quite normal, and number of things. But even the noise here is symmetric. So this means that under some cleaning, refusing of some cases, I can reduce this to a Gaussian. To the point that first I removed some noise just by doing this approach in measurement. I have now estimators, and there is a very nice article from a guy that is applying machine learning just because this is a Gaussian now. So its model learn by distinguishing the different Gaussians that he could find. It learns the Gaussian of the bad ones from the Gaussian of the good ones, and by reinforcing this learning, he is able to improve in time how many traces and measurement he needs in order to do that. So this is basically the state of the art. We have some limitation on what we can measure technically, because we need many. But we can reduce this measurement by cancelling noise and improving techniques on the analysis side. I actually invite you to read the article. It's really nice. So the research here actually has mostly focused on reducing the network noise, differential pairs, and network analysis. There are things which have been nice, because which time source do you actually use? I start my clock. Sure, which clock? There are many. This is also relevant. Someone actually said, okay, I would like to use the TCP timestamp as a measurement source, because every packet on TCP has a timestamp. Let me see if this works, because the timestamp is put on the victim side. So wherever it actually goes, the packet all around the world, the timestamp stays the same. So maybe I can actually do a number of measurements which are very close to the host. And also there are differential pairs, but unfortunately, no one actually focuses on reducing the noise on the host. Most of the measurement that you see in papers and in attacks, in blogs, are taken from user space, or even within a browser, within burp, in order to do SQL injection. And I'm not sure that, so that is sufficient for answering the need of the moment, but maybe it's not sufficient to assessing some risk that we actually going to see. So I actually focused on trying to reduce this noise in my measure. So what is the best clock, time source, and approach they can do? I think I've done something interesting, but I'll let you tell you this if possible. The measurement can be taken in multiple different path points. You are basically here at this point. While the packet traverses your network card, then is processed, is given into your through netdev in your SKBuf in the kernel. That's the first part of the interface. If you look at netdev.c in your kernel, this is where basically is the interface, is where from the hardware, the kernel, the packet goes to the kernel. Sorry, to the device driver, which is still part of the kernel. Then from the device driver, which lands here, is handed to the actual stack of the kernel, which is handed back to user space, and this is where you take your measurement, of course. So in principle, you might have in different point in time, different opportunities and different kind of time sources that you have. Different precision and accuracy, of course. The closer you are to the hardware, the less noise you have, and the more accurate you are. Of course, you might not have on the hardware clock which you go at 4 GHz like your CPU. Keep in mind that your network card, at least the one I have, which is an Intel E1000E, has a network clock at 24 MHz. I think I can overclock that at 96. I still need to find a way. Looks into some register, but I think I can do that. While in here you have a CPU clock at 4 GHz, which is completely different precision. The point is the amount of noise that you introduce this actually make your measurement go to the moon and back. From a CPU perspective. So basically all the research that we see on timing attacks happens here. And this is something which has really puzzled me for a while. Especially because now I have these opportunities with IoT devices. So I want to get the best out of it. User space measurement, this is the largest number of research. They are started as soon as packet is sent and stopped as soon as packet is received. Question, what do you think is the best precision that you can get here? Precision, meaning that... Sorry?
Is it unknown because you don't know if the kernel's tune your kernel with interrupt coalescing could be turned off?
Yeah, but from a time source point of view, apart from that, no, I'm not talking about accuracy, I'm talking about precision. So, okay, do you get a microsecond or a nanosecond? Or sub-nano? What do you get, you think? Well, actually, you get all the three possibilities. If you actually read the clock normally from your user space, as I'm talking about the Linux kernel, the clock actually gives you back answers in microsecond. So basically, if you look at the time spec structure that you get, it's micro. So even if your clock can go faster or your CPU can go faster, this is what you get. Recently in the kernel, they've been introduced also nanoseconds precision for the clock. But unfortunately, the clocks are not intended to provide this precision in a stable way. There is no guarantee that they don't drift. There is no guarantee that basically they will stay stable for a certain amount of time. So another important thing that you can actually use are not the clocks which are provided. You just start using CPU performance counter, and they go at the speed, of course, of the CPU. So in principle, if you start using exactly the same perf counter that's, of course, I mean, people like Daniel Gross and other people are using for doing cache timing attack, I have the same kind of resolution. Why shouldn't I be able to use that? In fact, I can do that. So basically, I have both the micro, the nano with the new structures, and the sub-nano with the performance counter. So I can actually choose. Someone might think that this may make a difference. Sometimes it does, but sometimes may not. The point is that the accuracy may be low, and that's a good suggestion. Doing interrupt coalescing, you can actually, but there's not much that you can do from user space still. You're still subject to the scheduling, you're still subjecting to preemptive, being preempted by other processes. It's not much actually that you can do. But still, there is a very easy way of getting the performance counter nanosecond from Python. This is really, really convenient. And it took me a while to find an easy way of doing this, because it is supported in Python 3.7 only. Because all the time.clock are deprecated from, because they are not good enough. It was about time, I would say, in a way. But you can access them from Python, and this is what I actually use in my tool. So because I'm taking measurement in a different situation, and I'm perfectly fine in understanding the limitation. Before choosing, you need to understand. So basically, I get nanosecond precision, and I have the performance counter. Of course, there are caveats here, because there may be an additional delay because of the Python interpreter. Of course, before the packets arrive to user space and it goes to the socket, and it goes to my Python user space and interpreter, and then I get, yes, you received the packet, there is an additional time. But if it's constant, if it's more or less constant, which is a big assumption as well, should be fine in a short amount of time, because I'm doing differential pairs analysis, and this means it cancels out. So this solves me a very nice part of the problem, this approach, because it does not cancel only on the network, cancels all the constant noise everywhere. So this is a very big change, in my view, in the way we do it. So you see, this is actually really look quite nicely. I mean, it's quite sharp. The average deviation that you have in this case is 82,000 nanoseconds, or 82 microseconds. Keep in mind, we are trying to measure a difference of 1 microsecond with a standard deviation of 82. Still, it's not that far. There might be much worse situation, which we have seen before. Basically, it was not even a Gaussian before. Now we have something symmetric, something that we may be able to statistically analyze. So this is user space. I worked also with kernel measurement. I didn't spend too much time because, of course, I have limited time for the presentation. I will be able to even show, because I have that in a demo. I can actually show how it works. So how will you take kernel measurement? I'm interested in your solution now. So basically, I'm sending a packet. I would like to know when it's sent or received, when the kernel sees that or receives that. Well, how would you do that? Please.
Does the NIC interrupt the processor?
Sure, that's the one. Involves quite some kernel coding, I think, and there is some module. I think that sometimes having the right questions is also important, because you would like to access the time source in kernel space. So my question is that how does Wireshark do? How does Wireshark that runs in user space take the kernel timestamp, the timestamp at the kernel level of the packet? Because if it does it, I can also do it, right? Makes sense? The timestamp of Wireshark are not done in user space. We agree, right? So they're done in kernel, but Wireshark see it. So if you actually dig a bit in libcap, you find out that the packets which are timestamped by the kernel, you can still also access it. And the nice thing is that in your library, you can set some callbacks that says, when you see this packet, please accept the structure and get out the timestamp that the kernel has seen. If you do like TCP dump, you also see the timing back and forth. And they are given by the kernel. That's why most of the research before actually does this test, start a sniffer, and then correlates all this stuff. I said, this is not for me, I don't like it. So basically what I did is that I started a different server, so a different thread, a different process that was actually listening in real time to what I wanted to see and capturing all the information and correlating directly. So basically now I have a situation where, and this is an important part I think, the analysis part and the collection sits on my host, while the measuring part can sit anywhere in the world because they communicate over socket. So think about that ICS network that has been compromised and I can inject once in something like that. Then immediately I go bypassing 2 continents in this way. And then the measurement is done locally, again, and not remote. Because if I inject this server, which takes the measurement in this way, even user space will be fine with that. I will be able to take the measurement locally and the processing remotely. And this has not even been considered yet at the moment, but I do have a working solution for that. So I can show you that. So basically I can install callbacks on packet reception sending. What do I need? Root privilege, nothing more. On a remote host. And I'm pretty sure that everybody in this room thinks that this is not so rare. The newest version supports nanoseconds precision. Let me show you the code, because it's better to show the code when we're talking. You do this. You see this? Timestamp host. This means you are asking the timestamp from the kernel, given by the kernel. Measure taken by the kernel. And the precision asking is nano. This is fine. I have to say that I don't have the picture I can show you real time, but the average distribution is still the same unless I do some tuning. I'm using a real-time kernel, by the way, so just to make sure that our ground is set. But it's another thing which I was interested in for a long time. We have now Ethernet cards that have hardware timestamps, and they are starting to appear in laptops. My Dell laptop has this kernel, has this card. So if you do actually that command, you see that you support timestamping in hardware of sending, of TX and RX, both in hardware and so I should have highlighted this too. So I can timestamp the packet when it's sent. And this is impressive, because usually you can do that when you receive it. So there are structures a bit complicated that you can access in order to get this timing. Of course, I mean, we also always look for the point of the weakest point. And I wondered, is this supported by any user space tool? Sure. TCP dump already supports that. So if your card supports this, you can pass parameters to say, I want to have a nanostamp precision on the hardware timestamp. This means that basically my kernel scheduling becomes completely irrelevant. Completely user space irrelevant. Let me show you how can that be done. It's the same way. It's actually the same structure. I need to just change a few lines until one line, one macro, and these timestamps are provided directly by the network card. As I said, there are a few caveats here, but with nanosecond precision. As far as I know, this is the first time which has been applied to timing attack. I just need to change these parameters, and if my card supports it, I get it. Let me show this. It was 80,000 before, and now it's 6 times more precise. I don't get it. This has been done while I was using a browser, while I was doing all these things. It's much better than the kernel measurement already. I did Skype active on this. I was actually doing stuff nicely. So what are the problems here at the moment? I need to wrap up, as I've been told. The demo, I'm going to show you that if you want to see that in hardware in the CTF, that you can join. It's the same demo that I just described. I have 8 digits of PIN, and this is what I got. Instead of having 8-digit PIN that needs to be found in 100 million attempts, I can do that in 2 million with the differential pair counted, okay, which means basically 1 million attempts, which is 2% of the space that is needed for brute force that. I can actually show that real time. For a slower clock, because this is 1 microsecond difference, if we go to 10, like an ICS device, I take that in probably 100 attempts. And I can show that real, if you come to hardware CTF. Questions? Done. Okay. I will.
You'll be at the hardware CTF, right?
Sure.
So yeah, people can probably, any questions you can.
Thank you very much. I hope it was interesting.